Hi, physics. Mr. Janowski here. This is the third part of the Chapter 8 slides. So remember last time we were talking about Clark W. Griswold falling off of a ladder and landing either on the driveway or landing on the lawn. So what would be the same in both situations? The impulse, J, which is the same thing as his change in momentum, would be the same in both situations. Now, something is clearly different. What would be different between these two? It would be the times and therefore the forces. The forces ultimately are the important thing. But basically, in the two situations, the time that the collision lasted, meaning the time in which Clark Griswold got the impulse, would be different. It would be much longer time if he lands on the lawn, and therefore a much smaller force on the lawn, which is why it's better to land on the lawn than it is to land on the driveway. But in this kind of thing, the key idea is the impulse, meaning the change in the momentum, would be the same. It's the time and therefore the forces that's going to be different, that are going to be different. So think back to the conservation of angular momentum demonstration. Well, we didn't actually do that because we're doing remote learning, which is a shame because it's a fun one. But anyhow, that law there, sigma L initial plus delta L equals sigma L final, that's the law of conservation of angular momentum. L with a hat is the symbol for angular momentum. So what's the law of conservation of momentum? It looks very similar. Sigma P initial plus J external, which is the same thing as delta P, equals sigma P final. So the sum of your initial momentum, which is sigma P initial, plus any change in momentum from outside the system, that's the external part of J external, equals sigma P final, the sum of your final momentum. And we can look at this and try to understand this idea by looking at two different phases in the break of a game of pool. So the first part of the phase is going to be the cue stick. Even if you don't play pool, you probably know enough about the game to know that this is the cue stick. The cue stick is going to strike the cue ball and send it moving this way. So that's the first part of, that's the first phase. The second phase is going to start with the cue ball moving this way towards the rack of balls. And then it's going to end with after it hits the balls and all the different object balls are now moving in all different directions. That is the end of the second phase. So in the first phase, initially the cue ball and all of the object balls are at rest. Those are the things that make up our system. The one cue ball, the white one, and the 15 object balls. Those are the solids and the stripes and the 8 ball. So at this point, nothing has any velocity, so there is no initial momentum. So sigma p initial, the first term over here, well, that just equals 0. Now, in this first phase, we are going to have external impulse. J external is going to be the impulse we get from the cue stick. So that is going to add momentum to the system. So at this point, we know the two terms on the left side of the equal sign. Sigma p initial is 0 because nothing's moving, nothing has any momentum. And J external is going to equal J cue stick, the impulse we get from the cue stick. And then the right side of the equal sign, sigma p final. Well, the only thing in our system that's moving at the end of the first phase is the cue ball. So sigma p final is going to be p of cue ball final. So put it all together. Sigma p initial, well, that was 0, plus J external, well, that was J of the cue stick, the impulse we got from the cue stick, and that equals sigma p final. And the sum of our final momentums, well, there's only one thing moving, so it's the momentum of the cue ball final. So that's the first phase. In the second phase, it's going to begin with the cue ball moving towards the rack of object balls. So it's going this way. Then it's going to collide, and the end of this phase is going to be now the cue ball and all the object balls are moving. So initially, sigma p initial, the only thing that's moving at the start of this phase is the cue ball. So sigma p initial equals p cue ball initial. Now, in the second phase, we're not getting any impulse from outside the system. In the first phase, we did. The cue stick hit the cue ball, but that's in the past now. That doesn't matter. That doesn't matter anymore. So we're not getting any other external impulse. So J external is 0. So we now know the first two terms over here. Sigma p initial is p cue ball initial plus J external is 0. Now, the right side of the equal sign, sigma p final, that would be a bit of a bear to actually do. So fortunately, we don't have to do it. But at the end of this phase, there are 16 separate things that are moving. The cue ball and the 15 object balls are all moving. So sigma p final is going to be the sum of all of their momentums. Momentum of the cue ball final plus momentum of the 1 ball final, et cetera, all the way out to momentum of the 15 ball final. So we would have 16 terms on the right side of the equal sign. And more than that, because P is wearing a hat, it's a vector, we have to pay attention to the direction. So the x direction along the length of the pool table, we'd have to figure those components out. And the y direction, which is like sideways across the pool table, not, technically up, above the pool table. Yeah, we'd have to figure those out too. So you would have to do 16 separate step zeros to get 32 total components, then break it up into an x side and a y side. You do all that stuff together, and if you did it and you had all of your measurements perfect, you would find out that momentum was indeed conserved in this situation. So after that, we watched this video about collisions. We watched half of it. The second half is on the center of mass, and we're not going to talk about center of mass right now. So I'll put a link to this video in the description to my own video. And yeah, you can watch it. Watch the first half up until she starts talking about center of mass. So in this video, we're trying to figure out what is conserved in a collision. Turns out momentum is conserved in a collision. Momentum is always conserved. That is one of the laws of the universe. That is a very one with everything kind of truth idea. Momentum is always conserved. Now, what is an elastic collision? An elastic collision is a collision in which kinetic energy is also conserved. You know that momentum is going to be conserved because that's always true. Elastic collisions are a special, subset of all collisions where kinetic energy is also conserved. An inelastic collision is just a collision where kinetic energy is not conserved. And then a subset of inelastic collisions are the perfectly inelastic collisions, and those are collisions in which the objects are stuck together at the end. So that doesn't happen in pool. The two balls don't end up stuck together in any meaningful way. But in this video, she was doing it with magnets. One magnet wasn't moving. It got smacked into by another magnet. Well, now they're stuck together. So that's a perfectly inelastic collision. The example I talked about in class was if you're standing there on a skateboard and I were to toss a bowling ball to you and you were to catch it, well, now you're stuck together. You are stuck to the bowling ball. So that would be an example of a perfectly inelastic collision. So again, in all collisions, momentum is conserved. In all everything, momentum is conserved. Momentum is always conserved. Momentum is neither created nor destroyed. In your elastic collisions, kinetic energy is also conserved. If kinetic energy is not conserved, you have what's called an inelastic collision. And in some inelastic collisions, the objects end up stuck together at the end, and those are called perfectly inelastic collisions. And I also pointed out that in the real macroscopic world, some kinetic energy will always be lost. There's always friction, heat, deformation, and sound. All of those things require energy, and that energy is going to be taken out of the initial kinetic energy. Some of your initial kinetic energy becomes those things, those other forms of energy, and therefore no real-world collision on the macroscopic scale is actually perfectly 100% truly elastic. Often you might get a problem where it's close enough that to simplify the math, you just pretend that nothing was lost. No kinetic energy was lost to friction, heat, deformation, or sound. But macroscopically, something actually always is. Now, microscopically, you can have elastic collisions. If two particles are bouncing off of each other, that can be elastic. Macroscopically, never actually happens. And then there was this video, which I won't even link because I don't like this video. I don't know why I don't just get rid of this slide. I didn't show this, this video last year, but whatever. Skip this one. So finally, to review, what is the symbol for momentum? P is the symbol for momentum. Your symbol for impulse is J. P and J are both vectors, so they're wearing hats. What are your units for momentum? Well, momentum equals PV. I'm sorry, momentum P equals MV. So it was going to be the units of M times the units of V, kilograms meters per second. So by now, most people have that. The next one is people get confused on. What are the units of impulse? Well, it's got the same units as momentum. It has to. Impulse is a change in momentum, so it has to have the same units as momentum. And then what is the law of conservation of momentum? Sigma P initial with a hat plus J external with a hat equals sigma P final with a hat. That is what all of your conservation laws look like. Basically, the left side is the initial side. That's the before picture. And the right side is the final side. That is the after picture. And if your thing is conserved, what that means is nothing was created or destroyed. So you have to have the same amounts before and after on the left and the right side. So again, what is conserved in a collision? Momentum, because momentum is always conserved. What is an elastic collision? That is a collision where kinetic energy is also conserved. An inelastic collision is a collision where kinetic energy is not conserved. So some kinetic energy ends up being lost. And then finally, what is a perfectly inelastic collision? That is a collision where your objects are stuck together. So that is part 3 of the slides. And then in class, I did homework 3, problem 1. Well, we did it. It was a we do. We did homework 3, problem 1 as a we do. So I'll make a video for that too, and look for that on the playlist. And hopefully you found this helpful.